All right, thank you very much. And yeah, welcome everybody. In the next 20 minutes, I will tell you what we did in the last year since ORCA 6 in order to enhance usability for our users and to make it easier to use a few of the significant features that we have. First about myself, so I'm here for FACCTs. FACCTs is short for Fast and Accurate Computational Chemistry Tools. We are a spin-off of the Max Planck Society, and we are working very closely in partnership with the MPI für Kohlenforschung. Our main product and main workhorse is of course ORCA, and our mission is to bring the fast and accurate methods that we have within ORCA to bring them to industry. Just to present us here also, so you all know Frank and his team. So Frank, he's not just the founder of ORCA, he's the director within the Max Planck Society. There's a large team of great people working on ORCA, and the FACCTs team is based in Cologne. So we have now about 20 people, mostly quantum chemists, but also physicists, computer scientists, and so on. And we work in close collaboration also with industry. We are based in Cologne, which is quite close, about 1 hour train ride apart from Mülheim. And so we work quite closely together. We also have a large collaboration network around the globe. So you just heard Giovanni's talk, who's based in Italy, but also we work closely with Stefan Grimmer's group, who's also quite nearby in Bonn. And there's also a lot of other great partners. Also, some numbers that might be interesting for our community here is we at FACCTs, we measure each year, we analyze the citation to ORCA and also to other QM packages, and we in order to see how good we are and whether there's any changes in terms of the QM landscape. And what you see here is that measure. So we measure the number of citations to the respective software papers, and here we plot the citation share, and you can see that ORCA is growing quite nicely in the citation share, and we also have a big increase in the last years, and we are now approaching about almost 100K registered users. But now to the main part of my talk. So I will have a first part where I'll give you an overview on the features that we worked on in the last year to enhance usability. I will here refer mostly to some other talks, and in the second part we will have a specific look at one detailed feature and how we try to improve usability there. So first topic, and that's something that will also be handled at a later point in this session now, is our newly released Python interface to ORCA. So Python is a tool that has in the last years especially been gained a lot of momentum also in the computational chemistry community, and so there's a lot of people, especially also in the machine learning community, who are making use of Python in order to run their calculations. And so what we have developed with the team here, we call it OP, so for ORCA Python interface. With our OP team in the last year, we have developed a tool which you can use to set up, run, and analyze ORCA calculations. And so here, the advantage here is that you get a Pythonic access to QM results, and that's something that you can see here. So you get them directly into your Python environment, and then you can manipulate them further. This also gives you the opportunity to combine the OP with other Python libraries, like for example the popular RDKit tool or visualization tools like Py3DMO. And so that helps us to then easily visualize QM results within a Jupyter notebook or within a Python script. And so that way we can, like Giovanni explained before, we can create heat maps to analyze energy decomposition, local energy decomposition, and also to visualize molecular structures and so on. And also this helps us then so we can run a lot of different ORCA calculations, and then of course also other calculations one after the other. And so we can create entire pipelines, QM pipelines, and that enables us to also run very complex and QM workflows. This also helps us to to communicate with other tools, especially from the machine learning community that are coming out since the last years. It also helps us and helps you as users to run always the same calculation again and again in high throughput screenings. And also this interface can act as a layer between ORCA and other tools, where you have a standardized way of accessing these, accessing ORCA and accessing the results that come out of ORCA. We will release OP under an open source license tonight, together with when the ORCA binaries will become available. So it's available under this homepage here, and also in about half an hour, Hagen will also talk in more detail about the Python interface. Another aspect that we at FACCTs are often facing together with our customers is ligand design, drug design, but also catalyst design. And so here, in the last years, we developed more and more accurate methods. We got access to methods that can be used on large systems with a high accuracy, but also machine learning models help here to bridge the gap between QM results and experimental results. And in catalyst design or ligand design, you often go and modify your compound in a certain way. So some functional groups can be exchanged, and that's what I try to visualize here. So you exchange functional groups, and then you say, okay, how do the properties, the QM properties that I'm computing, and how do the experimental results change with these functional groups? And so it is important to be able to detect these functional groups in an automated fashion. In the next talk, after my talk, Nicolas will talk about the new fragmentator that we have within ORCA, which is also connecting to a lot of other tools, but which especially helps us here with detecting functional groups for these types of applications. So what properties can we look at? We can, for example, look at interaction energies between different functional groups. So I have a ligand, I have an active site, and I'm changing some of these functional groups, and then I want to analyze, okay, when I go through this series of molecules here, how do the interaction energies change? And Giovanni gave a very nice talk before my talk, where he outlined how that can be done. There's also a lot of other properties, like, for example, partial charges that we can sum up for entire fragments, and that way we can analyze the trends going from one molecule to another, simply by looking at the summed up charges for different functional groups. Now on to another topic, with our more and more accurate and more efficient methods, but also with more abundant, more available low-cost methods, especially from the machine learning area, but also from the semi-empirical area, the models are becoming larger and larger. And so these low-cost methods, they are getting more and more important to be able to get a quick structure optimization, to run conformational searches or for MD. And so what we developed, and what Hagen will also talk about, is the integration in a kind of a plug-in fashion of neural network potentials, but also other semi-empirical methods that ORCA does not have intrinsically implemented into ORCA, so that you can run all types of optimizations, NEB runs, conformational searches, using also these external methods, as we call them. So stay tuned. Hagen will talk more about that. He also has some very nice application examples. Now, once we have these structures, we want to often get more accurate results, more accurate interaction energies, more accurate properties. And in that case, a multi-scale treatment becomes important. So either what we can do is we use a regular QMMM or ONIUM approach, where we have the region of interest at a very high level and the remainder at a low level, or we can also generate cluster models. And in the second part of my talk, I will talk about our convenience features for these areas. Lastly, because these methods are getting more and more efficient, we can go to larger and larger systems. And so here we saw that our tools to manipulate structures, to optimize structures, to run conformational searches are becoming a bottleneck. And so that's why we have also invested a lot in making our optimizations faster, and also in making our conformational searches faster by introducing a type of coarse graining into these features. But now I'll come to the second part of my talk, where we'll have a detailed look into improvements to set up and run multiscale calculations. Since ORCA 5, we have a variety of multiscale features available, QMMM, onion methods, and also embedded methods. I will talk about the QMMM and onion methods here on my next slides. Here I'm just showing some examples where you see what you can use these methods for. So we have onion methods, which you can nicely use for larger systems like organocatalysts. Of this example has about 300 atoms. So here we can simply speed up the calculation, the reaction mechanism calculation, by looking in detail at a higher accuracy into this region here, which we treat at a high level, and the surrounding is simply a spectator to this reaction here and treat it at a lower level of theory. We can also look at RNA ligand complexes, and here, for example, run LED calculations in order to understand the binding mode of the ligand to the RNA. And this is then using onion models. We can also look at, for example, covalent binders and how a covalent drug is a drug which does not simply bind non-covalently, but it binds covalently to its target protein. And what we do here or what I show here in this part is a reaction mechanism calculation of a covalent binder binding to a cysteine in the active site of this protein. So these are all QMMM calculations, and when these systems get larger and larger, also the setup becomes a bit more complicated. So if you have a very large system and you have a very large QM region, then your input can easily look like this. So you have to define the QM region by providing the atom indices, and then if you have like all kinds of residues, side chains included, then that becomes quite complicated to set up. And if you further also want to optimize your system, then the active regions of such a calculation are usually even larger, and then it gets more complicated. And so what we want to do is, and that's more in line with the thinking of how a modeler who sits in front of the computer thinks about it. So I have a ligand, or I have like two atoms which are binding, and these are the most important parts of the system. And now I simply want to add like whatever is around there, what could also be important for my model at a high level. And so we have achieved this for this ORCA 6.1 release to use this type of input instead of this type of input. And in order to get there, we need different ingredients. And the very first ingredient is we need a meaningful fragmentation of the full system. And so here ORCA needs to know about functional groups of your molecule. Let's say you have an organocatalyst, you have a ligand. We need to know about, okay, what are the functional groups that it has, but also for proteins, RNA, DNA, we also need to know about, or need to know about the biochemical groups like amino acids or side chains, backbone groups, and so on. And so this is something that we can do for small systems, for large systems. And as I explained earlier, Nicolas will talk more about this in his talk later. So for now, for this talk here, for the purpose of this talk, we will take this as a given. So we can somehow split up the system into meaningful fragments, which can look like this. So we have here photosystem 2, 500,000 atoms. And then here we are looking at one chromophore in the system, and splitting that up into fragments can look like this. So these are the individual fragments. Chromophore is split up into its functional groups. And so now that is the starting point for our automated QM or active region determination. So what you as a user want to do is you want to define the core of your QM region. That could be the magnesium ion here. So I have a QM core atom, that's this atom, and I want to include like the entire fragment that it belongs to, and that's something we did not invent, but that's something that is a best practice in the literature, that you enlarge this fragment by all atoms that are in a radius of about 3 angstroms or more or less, depending on what you're looking at, and then include all those fragments that are in the surrounding. And then you end up with the QM region. And so I want to now guide you through this process, through the procedure that we have implemented into ORCA in order to make this happen, to come from here to the QM region. So the starting point is the fragmented system. And now what you as a user give is the QM core atom. That is the magnesium here. So that's atom number 7, that's magnesium. And then what ORCA does, it extends this QM core atom to the entire fragment that it belongs to. Next, what ORCA does, it adds all atoms that are 3 angstroms or less from any of these atoms of that very first QM core atom fragment. Now we get a QM atoms list, which we extend further by all atoms that belong to the same fragments as those that we have in the current list of QM atoms. And so now this yields already a quite meaningful or reasonable QM region. But now, since in ORCA, we are running QM-MM calculations with the linked atom approach. So that means we might have some groups here, like we might, what that means is we usually cut when we have a QM region, then there's a neighboring MM region, and then any QM-MM bond that is there is saturated with a hydrogen atom. But this requires that the bonds that we cut between QM and MM are single bonds and are non-polar. And so what if this current setup here does not give us a non-polar single bond? And that's why we have additional checks within our procedure. So we also look at atoms that are topologically too close. Let's have a look at this system here. So this is the full system, and now the QM region that we have before is simply this region. So now you can imagine when this is the QM atom, these would be the MM atoms, and now when we add the link atoms, they are all placed on the bond to the neighboring MM atom. Then we would, in this case, we would add link atoms here, they would get too close, and so we would really get into trouble in our QM calculation. And how do we solve that? We simply add the fragments that are these MM fragments that are too close to QM atoms. And so that's also an established procedure in the literature, and that's something we also implemented into ORCA. Another aspect is that we might cut between QM and MM, we might cut aromatic bonds, double bonds, triple bonds. That's also something we don't want to have. So what we do then is we also here extend the QM region. In this procedure, we do iteratively until we do not add any more QM atoms to the list. And that leaves us with the final QM atoms list. So now that's a simple procedure. How to use it? It can be used for any type of QM and active region determination. So as part of the QM-MM or ONIUM calculations, and an example input is provided here. So this is a QM-XTB calculation. What we do here is we define the QM core atom, we define the active core atom, and we also define the fragment procedure. As I said earlier, Nicolas will talk more about this. Now, another interesting feature or new feature that we have now available within ORCA 6.1 is the QM setup feature. That is a dry run calculation. So what it does, it simply sets up the QM region, the active region, and stops. So that way you can analyze, so it also ORCA it prints the structure file of the QM region of the active region. So you can take that structure file and then you can also analyze it with respect to its charge, spin states, and so on, and whether you have the right input. But also another nice property is that you also can use that resulting QM region structure as a cluster model. So you can use this procedure to set up your cluster calculations. We will have an example on that later. And that's also what I want to do now. I want to show you a few examples so that you understand what the power of this procedure is. So here we have an organocatalyst. That's also what we saw before. This is a Diels-Alder reaction. So we have actually two atoms, which actually more than two, but what we treat here is we take 2 atoms that are involved in the bond formation, and that's then defining our QM core. In this case here, we use a minimal QM region. That means we don't take the default 3 angstrom radius around this QM core fragments, but we take 0 angstrom around that QM core region. And that way we get this minimal region here. Now let's move on to a more complex example. This is an RNA ligand complex, which in this case, we want to run a covalent calculation. So here we simply take 1 atom of the ligand as the QM core as defined here. And then the fragmentation for the ONIUM setup is defined in the QMMM block. Now, what is important here is, so yeah, here we also see the fragmentation. We also see the ligand, how it's embedded in the RNA, and what this is the resulting QM region. So that's what comes out of this fragmentation procedure and this QM core atom here. And now what is important is that also for covalent, we can and we need to use fragmentation input. And the approach, how we implement it is quite versatile. So we have an additional fragmentation procedure that is outside of the QMMM block. So the QMMM block fragmentation is for the QM region and active region determination. The frag block is the fragmentation for the actual covalent calculation. So here you can use the same fragmentation procedure, but you can also use an entirely different fragmentation procedure. Now let's move on to a different example. So here we see a protein ligand complex. We have the ligand at the active site, and we also have here two atoms that are important for the binding process. So we define them here as the QM core. That's what you see here. Now, what is often done also in these multi-scale calculations is that one looks at how do the properties that I'm computing depend on the size of the QM region. And that's what you simply can control via this QM core extension keyword. So what you can do is you can simply set this to 1 angstrom. So that's the size of how large do we extend our QM core. You can set it to 2 angstroms, 3 angstroms, 4 angstroms, 5 angstroms. And then you can observe, okay, how do the properties of interest that I have change with increasing system or with increasing QM region size. And now to the last example here. So this is photosystem 2. We saw that before. This is a 500K protein. Here we are interested in, for example, an excited state calculation of 1 chromophore in this photosystem 2. So what we take is we take a central magnesium atom or magnesium ion as the QM core atom. And then in this case, I want to show how to actually use the QMMM setup keyword. So everything else is the same, but you just add QMMM setup, and that's the structure that you get. And what you also get from the output is the indices of the QM1 and link atoms. They are printed, and that means you can take those, and if you want to run a structure optimization, you can simply take those indices and set constraints on your optimization. And that way you have a constraint cluster optimization calculation. Now, we're already at the end of my talk, so I hope I try to show you that we now have a simplified setup for multiscale calculations, which should really give you the opportunity to save a lot of time in setting up these calculations. We also have now an open source ORCA Python interface. Hagen will talk more about it. We can also now integrate neural network potentials and other semi-empirical methods in ORCA via plug-in methods. Plus, I didn't talk about it, but this is also a lot enhancing usability. We have a very much improved ORCA menu that will be going online tonight. I want to thank everybody who was involved in this work here. So especially the FACCTs team and the people at the MPI für Kohlenforschung for the great work that was done over the last year. Also want to thank Andy Beck, who helped in a lot of inspiring discussions, and also the Bistoni group with the nice developments with LED and the feedback that we had over the last year in setting up these simplifications. And I want to thank you for listening, and I wish you to have fun with our new ORCA 6.1 version.